So good evening to everyone. I hope you are doing good. So how are you guys? All of you? So here we are with our lecture number 5 on wave on string. Okay. Hardly this topic will take 2 or 3 lectures more. Okay. So today in the yesterday class, what we have did, anyone? So we have deal with the various factor that affect the speed of wave. Okay. In gases and speed of longitudinal wave, how does it affect speed of sound, how does it affect with the increase of humidity, with the decrease of humidity, okay, with the increase of temperature, with the increase of pressure. That all we have discussed in the previous session. Okay, got it. Now if you talk about today, that what we are going to do, so basically the focus is to establish a relation between the power and energy of a wave, because energy, we know that the wave is a disturbance of energy or momentum. So if energy is traveling from one place to another place, we need to study that what is the amount of energy which is traveling from one place to another. Okay, and if there is an energy in energy per unit time, is we all know that it is nothing but power. So that also we are going to deal. Okay, after that we will study the interference and the principle of superposition before interference. Then we move to the interference and see what the results that we got. Constructive interference, destructive interference, that all we have to cover today. Okay, so do not worry. And also the reflection of wave. So these are very easy topics, easy to crack, and yet very important also. So it will help you to understand the concept of the wave actually. Okay, so are we good to go? Are you ready, guys? Anyone give me a thumbs up and all? Okay. Okay, Divyansh. Is there JNV Ramnagar student is also here? I hope so, but not. Okay, not yet. He has not joined. Okay, no problem. So we will start what we have. Now, the very first thing that we have to discuss today is the energy and power in wave. And first of all, what we have take here, what we will take, just a second. We have a rope here. Let's say this. This is the rope in the unstressed condition. In unstressed condition. Okay. Now the same thing we will draw in the upside when we give it a wave. Okay. When we give it a oscillation. Okay. So what is the shape now? The shape will become like this. Okay. Just a second. Got it? Now, what we have in our mind, that if each and every particle of this wave or this string, I will say, or this rope is in SHM, if it is a simple harmonic progressive wave that is developed in the string or rope. So we know that, and what we misconcept here, what we misconclude, that if this wave is a simple harmonic progressive wave, which means each and every particle is doing SHM. So what we will say, that its energy the total energy of the wave will remain constant. Okay. And also we will say that where the kinetic energy is maximum, the potential energy will be minimum for SHM. And same we conclude for this wave because it is a simple harmonic progressive wave. But here's the turn. This is a wave. Okay, this is a wave. Then keep in your mind that energy in wave is not constant. Why? Because wave itself is the disturbance of energy which is traveled from one place to another place, which means the value of energy is constantly changing. If we have 100 joule of energy here, that 100 joule of energy will travel some after some time here, after some time here at this place, at this place. So we cannot say that energy is constant in wave. Everyone got it? So energy in wave is not constant. Wave is not up to mark, but oh, I'm not a big artist. So this is a, let's say, just I will draw it in a stressed position. This. So first thing to note here, that energy in wave is not constant. Got it? Now, if you see this rope in this unstressed condition, and you take up an element, let's say this element has a length dx. Okay, got it? Now, if you say project this same element in the stressed condition, then what will you find? The length of this element has been increased, and let's say this increased length is given by dl. Got it? Because always remember, when there is a wave developed in a rope, so the length of the rope will increase slightly, or it will stressed because of the tension that we are developing in it. Okay, so due to this factor, let's say this is dx and this is the displacement of this particular particle here, let's say dy. So we can say that this dl and dx and dy will hold like this, dl, dy and dx. Now, since this is in a stressed condition, so there will be a tension in this position, and if it is stressed, there will be a tension. And let me use another color. There will be a tension in this way. This is tension T. Okay. Now, if there is a tension in the string, consider a case when we have studied the mechanical properties of solid. Then what we conclude there? We have a metal wire, and when we stretch it, it stores some potential energy in it. Got it? Now, this is also a rope, a solid material, and this is also going stressed. This is also in a stressed position, which means some of the potential energy has been stored in this. Got it? So some of the potential energy is being stored in this position. Now, firstly, what we will do? Now, what is the displacement? dl, because initially the length was dx, finally the length is dl. So what is the displacement in the length? Displacement in length, which is given by dl minus dx, because initially the length was dx, finally we have a dl length. So what is the increase? It is dl minus dx. Got it? Now, so what I'm talking about the potential energy. So potential energy, you know that it is nothing but the work done by a conservative or restoring force. What is the restoring force acting in this? The tension. Tension is the restoring force. When we stretch it, the tension start acting, and it, when we release it, it will get back to the original position because of the tension. So which means tension is acting as a restoring force in this expression. Now, if we calculate the work done by T, so it will be given by, what is the force? T dot, and what is the displacement due to this tension? It is not dl, it is dl minus dx. If anyone has any kind of doubt, they can ask any point of time, because this expression is very important. Okay, although you do not need to learn it, or okay, very good, Hima, got it. So this is the work done here. Now we know that work done equals to the potential energy. Look, actually the work done is equals to negative of potential energy, or you can say potential energy is negative of work done by conservative force or the restoring force. But here this tension is not developed by own self. String अपने आप से थोड़ी हिल रही है. String hasn't developed this wave by own self. So who is responsible for that? We. Because we are stretching it, we are giving it a wave position, we are doing the oscillation on the one end. So we are the responsible, and the force that is applied by us is not conservative. Got it? That is why this minus being vanish, because our force is acting opposite to this tension. Got it? So that is why this minus being vanished here. So work done is equals to the potential energy. Now, potential energy, since this is a very small displacement, so how much amount of potential energy will be stored in this? The amount of potential energy stored is very small. So we can write it as du is equals to T dot dl minus dx. Student, please focus on the lecture. Do not uh, text me like this. I didn't get it what you have written also. So please focus on the topic. Okay. Now, so this is the potential energy stored in this. Now what we can do, we can write dl in terms of dy and dx. dl is acting as a, कोई बात नहीं, got it. Please focus on the lecture now. So dl is the hypotenuse of this triangle. So we can write dl as T dot dl is square root of dy square plus dx square minus dx. Since these are very small quantities, so what we can do, we can take dx as common out. Take dx common, so it will become T dot dx. And when we take dx common, So here it will be, we have to take from the square root, we have to take dx square. And when it came out, it will become dx. So here we will have dy by dx whole square plus 1 into raised to the power 1 by 2. Anyone? Any doubt? Minus dx, and that dx we have already taken out. So it will become 1 here. Got it? Now we can write this expression as du by dx, which is potential energy per unit length. Because here we are only interested in these dx. And dx is nothing but the length of the string or the rope. So du by dx we are interested in. Now it will remain as t into 1 plus dy by dx whole square raised to the power 1 by 2 minus 1. Now we can apply the binomial expansion here, and we know that 1 plus x raised to the power n is 1 plus nx plus further powers. So we are only interested in 1 plus nx, because higher power of this dy by dx is getting very low value, is getting reduced, because dy is itself is a very small value. So t 1 plus 1 by 2 dy by dx whole square minus 1, and this 1 and 1 got cancel out. So du by dx we have as t by 2 dy by dx whole square. This is equation number 1. Okay. Now we know that the wave equation, or the displacement of particle which is in wave. So this particle we are interested in, which has a displacement of dy, this dx length element, it has a displacement dy. So y we can write a sine, let's say, omega t minus ax, because we will consider the wave is going in positive direction. Got it? Now if you calculate dy by dx, it will become minus ak cos omega t minus kx. Anyone? I don't think so. Okay, you have any doubt, because the differentiation of sine omega t minus kx will become cos omega t minus kx. And further, if you differentiate minus kx, the differentiation of it will come out as minus k, and that is why it is ak cos omega t minus kx. Okay, you put this value, put it in equation 1. So what do we have? Du by dx equals to t by 2. This minus got vanish out. A square k square cos square omega t minus kx. Okay. Now we have to replace this tension also. How we will do that? We know that in a string, the speed of transverse wave, because this wave is a transverse wave here, and speed of transverse wave is given by v is equals to t upon mu, where mu is the linear mass density, t is the tension. So from here we can write the value of tension as v square into mu. So this du by dx will become mu v square a square k square divided by 2 cos square omega t minus kx. Okay. Now, one thing you can also do, you can put the value of k here. K is nothing but, k is the wave number. K is the wave number, and v is the velocity. And we also know an expression here that wave velocity, v is the wave velocity here. is given by omega upon k. It is simple. The coefficient of time and the coefficient of x. The ratio of coefficient of time divided by coefficient of x gives the wave velocity. Okay. So it is v is equals to omega by k. Now, if you put the value here, it will become omega square over k square. So this k square will cancel out. K square. This k square and k square will cancel out each other. So you have mu omega square a square by 2 cos square omega t minus kx. Let me write it like this. This is equation number. Now this is the expression of potential energy per unit length. Now the same we will do for what? Same we will do for the kinetic energy. Now let's see. Kinetic energy. You are writing it now. Note it down for your future purpose now. It will help you a lot. Kinetic energy of small element. So this dx is a small element here we have taken. So the expression of kinetic energy is 1 by 2 mv square. 1 by 2 m here we will take dm. Dm is a very small mass. Okay. If the particle or the element is very small, so the mass of that element is also very small. So it is 1 by 2 dm into velocity square. Now, here, if I talk about this velocity here, just a second. This velocity here is the velocity of particle, which is doing this oscillation, because this potential energy is also is of this particle, which has a displacement dy at certain instant. So this kinetic energy is also related to this particle, and this particle has itself a velocity, and that is why this is termed as Vp square. Got it? Now, if you take this string, let's say this is the string that we have in the stretch condition, and the string has a length small l, complete mass m, and mu is the linear mass density. So for dm mass, we can say dm mass is nothing but mu into dx. Linear mass density, mass per unit length. For how much length we have to calculate the mass? For dx length. So that is why dm is equals to mu dx. Now put the value here. So we have 1 by 2 mu dx vp square. Okay. And this is kinetic energy. So we can write that kinetic energy, and that kinetic energy is also very small. So the kinetic energy per unit length dk by dx is equals to 1 by 2 mu vp square. Now for wave for particle velocity, we know that how to calculate this. We know that this y is equals to, let me change the color here. This y is equals to a sine omega t minus kx that I have considered is the displacement of particle. So if I differentiate it, dy by dt gives me the particle velocity, and it is a omega cos omega t minus kx. क्लियर है सभी को? एनीवन, एनी काइंड ऑफ डाउट? नाउ dk by dx 1 by 2 mu, you have to square this because it is vp square. So we have a square omega square cos square omega t minus kx. Got it? In the previous expression, if you will see, the same expression we have for potential energy. Mu omega square a square by 2 cos square omega t minus kx. dk by dx is 1 by 2 mu a square omega square cos square omega t minus kx. This is equation number 3. So two things to note here, that first is kinetic energy and potential energy in wave increase or decrease together. If you see that du by dx, second is du by dx is equals to dk by dx. Okay. So the concept that we have studied in SHM, when the potential energy is minimum, kinetic energy is maximum. But in this, if you see the wave, if kinetic energy is maximum, at the same time the potential energy will be maximum. Got it? Now, if you see this is a wave here, this one. Let we talk about this particle. This is at the mean position and it is doing SHM. So it crosses this boundary with the maximum velocity. Got it? And if you see that here at the mean position, the stretching is maximum. If you let we consider two particles, and we will consider it on the next page. This is the wave and this is in unstretched condition. So if you take this particle, which is at the peak point, so at peak, if you see the length, if you consider dx, so this should be equal. Here is also dx and dx is equal. But if you consider at this point, let's say here, this is dx. And if you take the projection of this dx on this particle, so you will see there is an increase. So at the mean position, if the particle is coming at mean position from the top, it has a maximum velocity. We know that. ऐसे ऐसे कर रहा है. Let's say this is the mean position. So it crosses this span. This is the mean position line. It crosses this span with a very high speed. And at the same point, if you will see, there will be the maximum stretching. Here the maximum stretching that we have. Maximum stretch means maximum potential energy it has stored. See, the kinetic energy is maximum. The potential energy is also maximum there. So that is why we cannot say that the energy here is constant. Okay, because energy is traveling at this position, the energy will become zero, because at the peak position, if you will see very slowly, I will tell you, if you see at the top, the velocity of this fan will become zero, which means kinetic energy is zero. And if you talk about the stretched, Because of the stretch, the potential energy will come. There is no stretch in this position. We can say that potential energy is also minimum, kinetic energy is also minimum. And by the definition of wave, we know that there is a disturbance of energy which is traveled from one place to another place. So let's say here at the mean position, we have this 100 joule of energy. This 100 joule of energy travel here, and when it move further, it will become 0 here. Again, it is gaining its value 100. So you will see that this 100 is going somewhere in the direction of wave. Got it? So this is very important. And let me write the third point here also, that total energy is not constant in wave. Okay. At particular position. For different position, you will get the different value of energy. I think it is clear to everyone. Clear है सभी को? Give me a thumbs up if it is clear to you. Very good, very good, very good, very good. Now total energy. What will be the total energy? Very simple. Total energy per unit dx, we can say that it is du by dx plus dk by dx. Do not worry about this expression. It is coming from E is equals to k plus U. So if you differentiate it, so d by dx equals to dk by dx plus du by dx. We will write it as de by dx, du by dx plus dk by dx. Now, du by dx and dk by dx, we know the same expression. So they will add and give mu a square omega square cos square omega t minus kx. So here, this expression is also telling you that this total energy is variable. It depends on time, it depends on the position. Got it? Now, what about the power? Power transmitted, because we can say there is a flow of energy, so there will be a flow of power. There will be a transmission of power. So power transmitted. Now we know that power transmitted is nothing but the energy per unit time or the work done per unit time. And here the work done is nothing but the energy. So power is equals to energy per unit time. Since this will be a small power, equals to, we can say, dE upon dt. If we multiply with dx and divide by dx also. So this dx by dt here, what it should be? It should be wave velocity or particle velocity? Tell me, each and everyone, and answer this question very rapidly. Dx by dt represents here the wave velocity or particle velocity, because in wave we have thousands, crores of particles. Anyone? Sundar, Hema, Divyansh. So Divyansh is saying it is a wave velocity. Only Divyansh. What about Yoga, SABC, Suma, Sashik, Stephen? What about you guys? You are also agree with Divyansh? So now we have JNV Sambhaji also. Okay, so Divyansh is absolutely correct here. This dx by dt is the wave velocity, because if you know, that the wave that I have discussed in the previous slide, we can take this one. So we have considered this axis also as x, and this is y, we have taken here y, and this is x. So the wave is traveling in x direction. So displacement in x per unit time gives the wave velocity, and the particle is traveling in y direction. The displacement of y in the axis of y changes. So dy by dt is the particle velocity, dx by dt is the wave velocity. So it is dE by dx into wave velocity. Now dp is equals to dE by dx is mu a square omega square cos square omega t minus kx into v. So you can write it as dp is equals to mu a square omega square v cos square omega t minus kx. This velocity is nothing but or this power is nothing but instantaneous power. Instantaneous power. Power at that particular instant. Okay. Now, if you talk about the average power in one cycle, average power in one cycle, because when wave complete one cycle, there is a one wavelength the wave has traveled. So we are interested in one wavelength, or in one transmitted to the wave or through the wave. Okay. So average power, we know that instantaneous power is nothing but mu a square omega square v cos square omega t minus kx. So average will be represented by this symbol, this symbol. And for now, for the sake, for the lack of time, you remember that the average value of sine cos slash cos and cos square omega t minus kx, or cos square theta, let's say in general. So the average value of sine and cos will be 0, and cos square theta will be half. This will you learn in the upcoming chapter of class 12th. So do not worry about it. For now, you will learn that you only keep this in mind, that the average value for one cycle, this term has average value 1 by 2. So average power, P average, we can say, is nothing but mu a square omega square v upon 2. So this is, you can remember, and this is for one cycle. Got it? To remember this, then we will move further. Now the next topic that we are going to is, anyone, if any kind of doubt you have in this topic, tell me. Or is this understandable to you? Now, intensity. Any kind of doubt, guys? If do not have any kind of doubt, you can give me a thumbs up and all. Okay. Okay. How average value of sine came zero? That is something that we need to discuss on a wide scale. If you will see the graph of sine is like this for one cycle. If I talk about, although it is continued. Okay. This is y and this is, let's say, x, and here y is equals to, just a second, y is equals to sine x. So we know that when x is 0, so y will be 0 because sine 0 is 0. When x is what? Pi by 2. So y is 1, which means this has a maximum displacement 1. This is minus 1. So this about here, if you talk about the average value, so average value is calculated by the formula integration of y dt divided by integration dt 0 to capital T, 0 to capital T. If you put, let's say you will consider y here as t, or you can say it dx also, and this graph will be drawn in capital T. Okay, so 0 to t y, if you put sine t, and if you calculate this expression by this expression, you will get the value of sine. Average value of sine will be 0. Because the simple way to understand that, for one cycle, whatever the amount we have in positive side, the same amount we have in the negative side. So this will cancel out each other. That is why the average value of sine cos is 0 in an entire cycle. But if you talk about sine square cos square, so sine square cos square means for, let's say, cos square theta. So we know that 0 to 90 there will be no negative coming out. But let's say for angle 120 degree, so cos theta square. So for 120 degree, it will be pi minus 60, 180 minus 60. And for that, cos will lie in the second quadrant, and second quadrant cos is negative. So there will be minus 1 by 2. But you square it, it will become plus. So whatever the minus you have in the cos value, these all gonna plus in this cos square theta. So the graph that you will get is like this. You just invert the negative portion in the upside. Take the mirror image of it and it will be plus side. Now if you talk about for one cycle, this is the one cycle completing here. After that it is repeating all the values that we have in positive side. So we will having a non-zero value of what? Average value. Got it? Now I think it is clear to you. It is clear, Divyansh? Okay. And it is very good to ask doubts if you have any. Let me rough it. Just a second. Okay. So intensity is nothing but the energy transmitted per unit area per unit time. Now let's take a feel of it. Let's say this is the energy traveling in this direction. The amount of energy I am representing by these arrows, and the direction of flow is also by these arrows. So let's say this much amount of energy is traveling in this direction. This is it. So what we will consider a perpendicular cross section to the flow of unit area. The area of it is 1 meter square. Okay. So now we have this particular cross section and energy is traveling like this. Energy lines is also crossing it. Now, for this unit area, if we take a watch and note down that how much amount of energy is flown through this area in 1 second, let's say the value of energy is being drawn in 1 second is this. यहां तक जो है energy पहुंच गई. So this much amount of the energy has been flowed through this object, through this unit area. Energy is coming in this way. And let's say in 1 second, it has traveled to this portion only. And if we take a slab and cover it up, so this much amount of energy we have, whatever this cube is. Okay? This much amount of energy we have. For example, this is not compulsory to take a square loop. You will say this is the cross section that you are taking. Okay? And let's say this is the energy is traveling. So energy is traveling 1 second, and you stop it. So this much amount of energy has been traveled from here to here. And if I consider another ring, so there will be a shape like this, a cylinder. And this cylinder contains energy. Energy flown in 1 second. And this much amount of energy is termed as intensity. This is the intensity. Energy per unit area, per unit time. Okay, got it? I think you have filled it now. Now we talk about the expression, the concept I have taught here. Now, so intensity we represents with I, energy transmitted per unit time, E by T. We have already seen it in this expression. What is the E by T? E by T is the power. So it is nothing but power per unit area. Got it? Now, I is equals to mu omega square A square V upon 2 into area. Now, why I have written area? This A is nothing. A is not area. This A is amplitude. This A is amplitude. That is why I have written this area. Okay. So we know that this wave is traveling through the rope. Let's say this is the rope. And this has a length L. Okay. And the area of cross section of this rope is, let's say, A. And mu and mass of this rod is M. So mu will be M upon L. So we will put the value of mu here. So what it will be? I is equals to M omega square A square V upon 2 into, now this is L into area, length into area. What it will become? Length into area. Tell me, what is the value of length into area of this cylinder? Very good, Yoga. It is volume. Very good. And one thing that we have also conclude here, that M 1 by 2 M upon V. V is the volume. Let's say capital V, or let's say we write it as volume only. Omega square A square V. V is the wave velocity. Mass per unit volume will become, yes. Mass per unit volume, density. Very good, Yoga. You just nailed it here. 1 by 2 density rho omega square A square V. Okay. Now, if you put the value of omega in terms of frequency, so I will be 1 by 2 rho 2 pi f square. So it will become 4 pi square f square a square v. So 2 and 2 will you can cancel out. It will become I is equals to 2 pi square rho f square a square v. And now this is the expression you need to learn. This is the expression of intensity. A very important point here to note down. पहले इसे नोट करो, note it down. And when you note it down, let me know if we have noted it down. Okay. So we can say important point here. Important point is this intensity is directly proportional to 1 by r square. And what is this r square? R is the distance from point source, from where the sound has been generated. This is the distance from that point. So if the distance increases, intensity will decrease. If the distance decreases, say you are very close to me, you put the earphone. So now my voice, which is the source point, you put the earphone here. Do you have a distance? Okay. So intensity is low, which means you heard a very low sound. When you put the earphone in your ear, the intensity is so large because the distance is decreased. Okay. So if the distance decreases, intensity increases. And amplitude of any sound is depends on 1 by r. Okay. So both the intensity and the amplitude will depend on the distance from the source point. Got it? Now, this is it for today, I guess. So the topic that I was thinking that I'd cover in this lecture, we will cover in the further. Okay. Not too much portion of this chapter is remaining. So do not worry about that. We will cover it. Any kind of doubt if you have right now, you can ask. Otherwise, the lecture is being over, guys. Thank you so much for being attentive. Okay. Bye bye, Yoga. Take care of yourself. Bye bye, Divyansh. Take care of yourself. Bye bye.